Now, in this example, we're given functions without the graphs and we're asked to find the points of discontinuity and to explain why. But I went ahead in this example and I'm going to draw the graphs. I want you to basically ignore the graph and think about the algebraic function itself. We're going to find all the values x equals a where the function is discontinuous. And the first function, part A, is f of x equals the rational function x squared minus x minus 6 over x minus 3. Okay. Now I know that when x is equal to 3, we have a zero denominator, and therefore this function is not going to even be defined at x equals 3. It's going to have a big hole. Other than that, it's going to look like a line. It's supposed to be a straight line with a big gap at x equals 3. But don't think about that. Think about the actual equation. Okay, when g of x, well, that thing's equal to 1, negative 1 over x squared whenever x is not equal to 0, and 2 when x is equal to 0. Okay, so it had this strange situation where 0 was undefined in the top graph, but it is defined in the bottom part where it says the y partner is equal to 2. So at one point it's equal to 2, everywhere else it has this strange asymptote thing happening. And the next one, h of x is equal to the same graph that we had for part A, the same function when x is not equal to 3, but then we defined it when x is equal to 3 as 2. So the picture would look very similar to the first picture, except at the point y equals 3, instead of just having an open gap, we're going to define the function as a single point with the y partner 2. And part D is the greatest integer function, you know, the step graph that we've seen earlier. F of x equals the greatest integer of x. And that picture, you know, was a step graph where it would have a solid point, move to the right 1 unit, then have an open circle, solid point, move to the right, open circle, so you could kind of walk up the steps. Okay, now once again, try not to look at the graph when you answer these questions, because in this type of question you don't have the graph, just the equation. Part A for solution, we have a discontinuity for that one at a equals 3. In other words, x equals 3. And the reason why is if you just look at x squared minus x minus 6 over x minus 3, what happens to the denominator when x is equal to 3? You get a 0 in the denominator, so f of 3 is undefined. The second equation, g of x, has a discontinuity at a equals 0. And the reason for that is if you look at the equation, although g of 0 itself is defined to be equal to 2, so it is defined, the problem is that the limit as x approaches 0 of g of x is equal to negative infinity, and negative infinity means the limit does not exist. And that's why it's discontinuous at a equals 0. Now for part C, we look at the graph and we see that, well, don't look at the graph, look at h of x. H of x has a discontinuity at a equals 3. And that's because the denominator, although the function h is evaluated at 3 is equal to 2, so it does have a y partner, it's equal to 2 when x is equal to 3. The problem is that the limit as x approaches 3 is found by simplifying the rational function. So you factor the top as x minus 3 times x plus 2, and then you simplify that rational function by canceling the common factor of x minus 3 on the top and bottom, and then you evaluate the limit as x approaches 3 of the remaining factor x plus 2, and you get 5. So it turns out the limit does exist at x equals 3. However, the function evaluated at 3, its y partner is 2, and that is not the same as 5, which is the limit. So the evaluation of the function does not equal the limit when x is equal to 3. Well, you got to have that for continuity. So this means that the limit, the actual function is discontinuous at x equals 3. And for the postage stamp or the step graph, we have discontinuities at all integers. The set of all a, such that a is an element of the integers. That funny looking z means the integers. This occurs because the right limit from the right side is not equal to the left limit. We saw that earlier, and that means that the limit does not exist for every integer a element of z. And if you look at the pictures, these answers all make sense, but you got to be able to see this without looking at the graphs. You got to be able to see it by looking at the formulas.